I begin?
Okay.
Yeah. Can I begin now?
Yep, please.
Okay, perfect. So hello, everyone. So just to introduce myself, I'm working at CMF in the ELISE team. So I'm a research engineer. I've been there for a few years now, and my focus at the moment is on machine learning and more specifically on the application of deep reinforcement learning to fluid mechanics. So today, what I've prepared is, so as you see, a short introduction to deep reinforcement learning, and then how it couples to computational fluid mechanics, and also, so that it's a very general introduction because, as you can imagine, deep reinforcement learning is a vast topic. We could be discussing the whole thing for weeks. So it's examples, a few insights of how we make it work, how we couple it with numerical solvers, a few words on the state of the art, and also a digression on the optimization method we designed a few years ago based on policy gradient methods. So we'll see how things evolve. So I don't really know the background of everyone that is watching this presentation. So if something is unclear, don't hesitate to interrupt me so I can clarify some points. Okay, so just to give a bit of context, what are we looking at? What's the position of deep reinforcement learning in the context of machine learning? So this is a very basic classification. It's not very accurate because depending on how you see things and how you consider things, that might be wrong, partly wrong, but it's a way of classifying things at least. So you have machine learning, which is included above in the more general topic of artificial intelligence, but it's a very narrow subset of artificial intelligence, machine learning. And you can see the two sides that we see usually, like the two topics we see usually, which is supervised learning, which is what we see every day in the news, like ChatGPT, a bit of ChatGPT, all the bots that you are discussing with, most of the applications in natural language processing, image processing, it's supervised learning. So I would say at least 80% of what's happening in machine learning is supervised learning. Then on the other side of the spectrum, you have unsupervised learning, which is used for some very different types of application, like compression, so autoencoders and stuff like that, and also automatic clustering, for example. Also, what we call representation learning, which is based on autoencoders and evolutions of autoencoders. So these two parts are what we are used to, like supervised and supervised learning. And in the middle, we have the third category, which is reinforcement learning. So I will be saying reinforcement learning. What I mean is deep reinforcement learning is just a shortcut. Deep reinforcement learning being the encounter of deep learning and reinforcement learning, because reinforcement learning has been there for decades, but mostly in the form of tabular approach or approximator approaches, but without the deep learning parts. Okay, so reinforcement learning is actually very old and has been there for decades. And so the let's say the zoology I present here, policy-based, value-based, we'll see that it's not very true. It's just a way of seeing things. Okay. So reinforcement learning is just like the outsider, more or less, of machine learning. But we'll see what we can do with it. So just to clarify a bit, supervised learning, you have you are trying to train a neural network to do a particular task with labeled data. So you have a big data set with inputs and labeled outputs, and you're trying to train your neural network as a mapping from the input to the outputs. Okay, so this mapping is more or less exact on the data points you have in your data set, and it interpolates in between. But you need labeled data, so that's the key point. You need in general a huge data set. So here, for example, the input would be this is from the MNIST datasets, and the input is here a handwritten digit, and the output would be like the actual value of the digit written here. So you're trying to train a neural network to recognize handwritten digits. Okay, that's the very common example. I guess many people in the room will know it. Another example for unsupervised learning. So you still have a data set, but you don't have labeled data. There is no ground truth to learn. You're just trying to reorganize or learn a representation of the input data you have in order to extract insights. For example, here you are doing clustering of housing prices. So the unsupervised methods is able to separate without additional data, separate the data set in two parts that represent the ranges of prices. Okay. And then you have deep reinforcement learning. So the goal of this deep reinforcement learning is to learn from observations on an environment in order to and take actions that will modify the environment in order to maximize a reward signal. Okay, this very simple example may also, if in the room people have given a look at reinforcement learning, you probably know the cart pole example. So you're just trying to keep the pendulum straight up by moving the carts left and right. Okay, so you have a joint here that is frictionless, and when the cart moves, the pole moves accordingly, and you're just trying to balance it up in order to keep it straight. Okay, so here the network is learning from what is provided to it. Okay, so observations in order to say, should I go left, should I go right, at what speed, in order to keep the pendulum up. Okay, so let's go to the general overview of deep reinforcement learning. So again, deep reinforcement learning is a vast topic. There are many different methods. Not everything, I will say, is true for all methods that exist in deep reinforcement learning, but we have to start somewhere. So I'll be going for the simplest ones. And if you will see that if you dig a bit further in deep reinforcement learning, you will discover that not everything I said today was 100% general. Okay. So this is a picture that you will see almost everywhere in reinforcement learning. So the definition I put at the bottom is pretty self-explanatory. You're trying to learn an observation-based control law using trial and error interaction. Okay. So what do we mean by trial and error? We mean that when the environment provides an observation to the agent reacts by sending an action. Okay, so the action will modify the environment, moving from a state to the next one, and the trial and error part is located in the reward signal. Okay, the reward is a way of measuring how well we did with the action when we were given an observation. Okay, so was the action beneficial to the goal that the agent has, or was it a bad choice from the agent? This is what the reward says. Okay, so the reward signal is very important because it tells the agent how well he did. Okay, and then the loop goes on. Like the environment was modified, new observation is issued, the agent takes a new action, the environment is modified again, reward is provided to the agent, etc., etc. So, for example, just to better understand, in our context, the environment was the card poll problem, okay, and the agent was, let's say, a set of neural networks that are trained in a way and that do several things. We'll see later that it can be one network, it can be several ones. They can be trained in many different ways. The actions can be issued in different ways depending on what kind of agent we choose. Okay. So a first differentiation we have in DRL is the model-free and model-based algorithms. So model-based, I won't be discussing that today. It's mostly dynamic programming and associates. I'm definitely not an expert in this kind of methods, and the issue of model-based is that it requires a model, and usually we don't have a model available, at least in all cases. So we, as people trying to working on free flow control, we are not interested in these methods. Model free means that we don't have a model of the environment, and we have to interact directly with the environment, the real one. So either a numerical simulation, an experimental setup, whatever. Okay, and that direct interaction means that we don't have access to cheap predictions. Okay, running one step of the environment is expensive, usually, whether it's experimental or numerical, and we can't foresee what will be happening later, which is usually done in model-based. In model-based, you will try to exploit several possible next steps to make a decision at the present time, which is possible just because your model is cheap to run. So you can say, okay, let's see what happens later if I take this decision now. In model free, you take a decision now, you get your next state and your reward, and you have to make a new decision directly that will impact your environment. Okay. Okay. And so in the model free panel, we have, again, different methods, different types of methods. So we have on both sides policy-based and value-based. So we see that these are the two very different approaches. But in fact, the state-of-the-art methods are not just policy-based or not just value-based. Today, most of them fall in between. They use both policy and values, and very often many different values, and they so are not this separation doesn't make much sense today. It's just to try to get a grasp of what was done at the beginning. Okay, so in policy-based, the very basic algorithm is reinforce. It's very just one policy and Monte Carlo updates. And in value-based, the basic algorithm is DeepQ network. So it's a full temporal difference update. And in between, you have actor-critic methods. So A2C, A3C, PPO, TRPO, and others. Okay, so yeah, the distinctions between policy-based and value-based just blurs with the increasing complexity of the algorithms we consider. Okay, so today we have many different existing libraries if you look on the internet, so this is just a sample, and it's quite an outdated sample, I would say, because today OpenAI baselines is not really in the trend anymore. Stable baselines, yeah, it's now the third version, I guess, based on PyTorch. Keras RL, I don't know if many people use it. It's just there because Keras was there. But today there are many new new libraries that are more trendy, I would say. So I would need to update this slide. I'm just like doing a bit of promotion. We are working on our own library because we are interested in, maybe because we do specifically numerical flow control. We are working on specific topics. So we have our own Dragonfly library in-house. Okay, and so most of these libraries, they have, it's very easy to just plug and play with simple environments. For example, in stable baselines, you could train a CardPool environment with a PPO algorithm in just 2 lines. Okay, so that's in many cases you can start playing with what exists very easily. From my own experience, trying to develop in these libraries can be pretty hard. So I haven't looked in very recent libraries too much, but stable baselines, developing in stable baselines was quite tough. So yeah, but you can use them as black boxes as long as you have environments available to process. So another word about a different library which is called GYM. It's not a deep reinforcement library per se because it doesn't contain any kind of algorithms. It's just providing a standardized interface. If we have developers in the room, they know that standardized interfaces are very, very important when you have how to say a community working on the same topics. And here, using the same standardized interface allows people to just swap environments and library easily. So you could have an environment written by yourself, for example, as long as it verifies the interface, you could train it with one library or the other. It wouldn't really make a difference. Like you wouldn't have to adapt, rewrite anything. It should work directly, which is a particularly important aspect of the working in community. Like let's say the deep reinforcement learning community has gone through a very intense reproducibility crisis, and for different reasons. We can discuss that later. And I would say a standardized interface was at least the beginning, the first thing to start with. Like it was very important to have that. So if you ever work on that, I would say this is important to. It is important to follow standard interface from the community. So today, GYM has become Gymnasium, but the interface hasn't changed. Okay, it's more or less the same. So I'll be giving a few examples now. We'll go through the first example we started with sooner, which is the CardPool one. So it's really a toy problem, and it's provided directly by the GYM package. Okay, and so as I said before, the goal is to balance the pool up. And it only takes discrete action. So that's you have to be aware that in most environments you have either discrete actions or continuous actions, and it makes a difference in the algorithms that you can use for that. Discrete environments are usually easier to learn because let's say the variability the action space is smaller. So by default, you would imagine that it's easier to learn, and it's often easier to learn given that the environment can be solved with discrete actions, of course. Okay, so here the pole can only the cart can only go left or right. Okay, it cannot be still. And so as we saw before here, so we have to define what are the observations, what are the actions, and what is the reward. Okay, so every time we present an environment, we have to say what are the observations, what are the actions, what's the reward. So I said, okay, the actions are just moving the cart left and right. The observations is just so the environment is very simple. So you could work with just images. You could make it work, but here it doesn't really make sense to work with images. So here you can just provide the position and the velocity of the cart and the angular the angular position and velocity of the pole. Okay, so it's four reals, and the reward is +1 for each step that verifies that the angle of the pole is within certain limits that are imposed by the environment. Okay.
Jonathan, may I ask you something?
Yes.
Is the reward like a dichotomous, like I don't know, or discrete, or should be continuous to make it upright position?
I'm not sure. Is the reward what?
Because I see you reward the algorithm +1 if the theta is between two boundaries, but then it doesn't serve any gradient information. Is it
That's true. That's true. Let's say that the environment is so simple and so easy to solve that it can be solved with a linear controller. Okay, in a very few steps. So this environment is so simple that this reward is enough. But as you say, we could say the reward is just the reward increases when the theta is close to 0, okay, and it gets lower when it gets away from 0, for example, in a way or another, like with a squat difference or whatever. But this was just designed like that. I wouldn't have done it like that. It's not. I didn't write it, okay, as it's provided in the GIM package, but it's actually done like that, and it's sufficient. It's actually sufficient. But of course, you will see that reward design is one of the toughest parts of deep reinforcement learning. You have to think. It seems simple, and it's actually one of the hardest parts.
Yeah.
So on the left, what you see is a poorly trained agent. So it's on purpose. It doesn't work really well. Like it struggles to keep the cards up. To do that, I just trained an agent for a limited amount of time, like a few tens of steps, a few tens of episodes. We'll see later what episode means. Okay, so it works, but not perfectly. And on the right, it's a very well-trained agent, like it barely moves. We could do even better, like the agent slightly moves to the left, but it could be even better. Okay. So the typical training time with PPO, so one of the algorithms that we use, 100 episodes, so 20,000 transitions. Transition is one observation, action, reward. Okay, that's one transition. Okay. So as I said, this environment is extremely simple, and 20,000 transitions for that's actually huge, because deep reinforcement learning is not aiming at such simple things, I would say.
Jonathan, may I ask a question? Yes, I'm trying to understand what is this GIM package. You mean this environment, what you call environment, are actually models that are inside these packages that you can use for? Okay.
Exactly. That you actually have this is a simple mechanical setup. You can write the equations for all this. So the impact of the movement of the pole on the movement of the cart and vice versa, and write the time integration of all this. It's a simple it's two coupled ODEs, and then you just integrate that. That's what's happening in the package. And in fact, the Gym package provides different simple environments for benchmarks. It's mainly for benchmarking. So yeah, 20,000 transitions for that's a lot, because you could solve that in 1,000 transitions with a linear controller or a PID controller. But at least you can try. It's just about checking that your algorithm works. We have much harder environments to check that everything works, and that to check the performance of your algorithms. For example, Atari games. So this is more or less so this is from a paper of 2013, and this is more or less like the first breakthrough of deep reinforcement learning. Okay, so it was this paper playing Atari with deep reinforcement learning, and it was introducing DeepQ networks and evolutions of like the refinements of DeepQ networks, which are the first basic algorithm we usually learn in deep reinforcement learning. And so in this case, the agents were learning to play the games directly from screenshots. So your observations that are provided to the agent from the environment, they were just screenshots of the games. And in fact, the agents learn to perform insane scores on many of these games. Like the list is very long. I don't remember, maybe 100 and something games that are all packaged in Gym. And in fact, you could get very interesting things with that. So it was the first breakthrough of deep reinforcement learning. It seems stupid to play on Atari games, but in fact, there is a good scaling of complexities in these games. Like you have many different cases where you have immediate rewards or delayed rewards, latency, very large amount of actions, etc., etc. So it was actually very, very impressive. So on the left, an agent that hasn't learned anything, so it's a random agent, it does nothing, and so you see that the game starts, the ball falls out, and the episode is terminated immediately because it does random things. And on the right, a train agent that performs a very good score actually. So it moves a bit randomly sometimes, depends on what's happening, but it still works very well. But these ones I did not train them. This one I took it on the internet just as an example, because training can be quite long. As you can see, DeepQ network took between 10 million and a few tens of millions of transitions for each game. And we are not really interested in spending too much time doing that, because it's not really, like I will say later again, the benchmark you consider is important. And in that case, actually, this benchmark is not suited for problems. But it's very interesting. Okay. Another example that has been seen a bit in the news a few years ago, like I would say 6-7 years ago, and that is still very used today, is locomotion behaviors. So we have some sort of, not humanoids, but beasts that can move. And the agent has to learn to move forward with these beasts, okay, by actuating the joints of the animal, okay? So depending on which one you're considering, you have different amount of joints that can be actuated. So in this one, we have only 3. We'll see that it bends in 3 positions. Here we have 8 or maybe a bit more than 8, I don't remember. And here even more. And you can have, like, you have a real humanoid with 20 joints or more. so that the action, let's say the action space becomes very large. The observation space becomes even larger. This is full continuous control, and so you see that observations, you have joint angles, angular velocity, global velocity, acceleration, contact sensors, and more. Okay, and so the goal is to move forward without falling, and with a decent velocity. Like moving too slow is also that doesn't bring a good reward. Okay, and so typical training time with what is called soft actor critic, which is still a very it's not very recent. Like it has now 4 years, if I'm not wrong, 4 years. So 4 years in deep reinforcement learning is like a decade or more in other fields. But 1 to 5 million transitions, depending. So these ones I trained them myself with a soft actor critic algorithm that I wrote. Okay, it's almost state of the art. It's not perfect compared to the literature, but I don't have tens of GPUs available, so I'm not spending my time training little beasts to walk. Okay, and again, these environments are available in the GYM package. Again, it's very recent because before that, it's called the Mujoko package, and before that, it was not free and it was held by a team. I don't remember where, and now it has been bought and made free to the community. So this one is called Hopper. So it has 3 joints, and it actually just hops from one spot to the next one. And so what is important to get is that the algorithm learns this locomotion behavior from scratch. Like at the beginning, the first thing the agent does is just falling all the time. And with many transitions, you see a few million transitions, if it eventually learns how to progress. Okay, and in this case, I have to underline that the reward design is like of utmost importance. This is a sort of spider that learns to walk very fast. It actually cheats a lot because it has 4 legs, but the best rewards are obtained when it doesn't use the rear and the front one. Okay, and this is called half cheetah, and it's a sort of balance 4-legged animals but with only 2 legs. Okay, and this one works really well. It's one of the simplest to learn is this one actually, even if it has more actuations. Okay, and this has been first seen in this publication, which was quite a breakthrough also after the Atari stuff. So just a small timeline. So as you saw, DQN was the Atari things. Soft actor critic 2018 it was here. In between, we had DDPG, which was an evolution of DQN for continuous environments. Then in the same vein, DDPG evolved in TD3, and in the same year, soft actor critic was released. TD3 soft actor critics have, in some cases, similar performance levels, but most often, I mean, soft actor critic is still a bit preferred by the community, from what I heard, from what I understood. And so why is it orange? Because it's off-policy algorithms. Okay, so I won't extend too much on what is off-policy, on-policy, but the training and the design of the methods are very different from off-policy to on-policy. It's very different. Off-policy is supposed to be more sample efficient, while on-policy is supposed to be more stable. My word on that is that it depends. And it depends a lot on the environments you're working on. And in fact,
Alors,
of boxes stacked together that work together. But for the main algorithms, so there are now more. I should complete on the right. There are a few more, but I would say there has been an intense decade from 2013 until today, and now it's more like we're in the applicative part. Like the following decade will say, do we keep reinforcement learning as a useful tool for control, or is it not suited? Like, is it too much of a burden given what it provides? And this can only be discovered by trying to apply it in real life, which is what we are doing. Like, we are trying to work on flow control with deep reinforcement learning, and this is, it needs to, we need people to focus on that, just to see, are we crushing existing control methods, or are we just like doing more or less the same with a fancy tool that didn't exist before? Okay, that's the question. For now, we have good hopes because we've had several breakthroughs in the community of flow control. We need to pursue on more realistic and industrial applications. That's what you need to remember about that.
Jonathan.
So, yes.
May I kindly ask you, could we have a break now? Because according to our schedule, we would have a break from 10:30 to 11.
Okay.
Would that be possible?
Yeah, sure.
Yeah,
sure.
Then maybe we can start again at 11.
Okay. I wasn't aware of that, so yeah, no problem, of course. Okay, so let's have a break now, and we start again, yeah, at 11, no problem.
Okay.